Thanks. Good. Hi, good morning, good afternoon, everyone. Today we have the honor to have Dr. Cogan Shimizu from Wright State University to give us a talk about his recent work on knowledge graph and ontology engineering with large language models. Dr. Shimizu originally finished graduate study with his supervisor, Dr. Pascal Hüsler. I believe many of you know him. And then after that, he finished postdoctoral training in the enslaved peoples of the historical slave trade and also the low-wear graph research projects. And currently at Wright State University, his research interests include knowledge graphs, ontology modeling, engineering methods, and also ontology design patterns, and the fancy word called neuro-symbolic AI. I think some of you are also working on those. So today's schedule is like this. First, Dr. Shimizu will give a talk. You can actually already see the title on the shared slides. And this will be about 30 to 40 minutes. And after that, we will have about 10 minutes for questions and discussion. So hope this is clear. Next, to save some time, I will just give the floor to Dr. Shimizu. Yeah. You can start when you are ready.
Hello, sorry, my Zoom just froze. Is it time for me to start talking now?
Yeah, now it's back.
Okay, cool. Sorry for that. I'm in I moved like where my Wi-Fi adapter is and everything, and it's been giving me some trouble. But yes, thank you very much for the introduction. Yeah, like you said, I know my connection to this community is through Pascal, so I'm sure you've met him, but also many others in the community like Adila and Michelle Cheatham back in the day, and Colby Fisher, who is with me on the Noah Graph project. So it's really quite a pleasure to be able to talk with you guys and speak a little bit about the various advances that we've been working on in the development of engineering methodologies for knowledge graphs and ontologies, and specifically, as is all the rage these days, right? Large language models. And so we'll start with a little bit about me. Or well, an outline first. So just a little bit about me and then kind of talk about some of the other things that I want to do. And then we'll move into modular ontology modeling, which is kind of the basis for these accelerating principles, you might say, and then exactly what we'll do with or where we've been able to apply this and see some outcomes. And then I have a couple questions if we have time, just to kind of drive some interaction. So as you introduced, my name's Cogan Shimizu. I'm an assistant professor at Wright State University in Dayton, Ohio. Not close enough to the floods, thankfully, and our own rivers aren't doing too much, so pretty safe in that regard. But yeah, and I work in the Castle Lab, or the Knowledge and Semantic Technologies laboratory. And we do all sorts of things. We're working on essentially the whole pipeline from building a knowledge graph, equipping it with a schema, materializing it, and then doing something with it, whether that be teaching, whether that be domain-focused work, or if it's building tools that help us do any one of these components. So the question then becomes, why modular ontologies, right? Every knowledge graph that we make in the Castle Lab is a modular ontology, and modular ontology comes out of my dissertation work that I did with Pascal and builds on a lot of work going all the way back to, for example, GeoLink, which many of you might be familiar with. So why exactly modular ontologies? So at the risk of reading this particular slide to you, it's that the modules, as we think of them in terms of ontology, are essentially human partitioned subgraphs or subontologies of the larger ontology that essentially correspond to how a human would conceptualize a particular topic, right? So we call this a bridge, right? A bridge between the machine readable data and the human conceptualization or the human knowledge. And what this does is it helps us provide a structure, right? A little bit more of a superstructure to the ontology, such that it allows us to say, if we want to evolve a certain aspect of the ontology, we can connect it very directly to specific modules, one or two or more, but probably just one or two, um, based on that knowledge partition. Now, the other thing that we want to focus on is that modules, because they're by their nature mostly self-contained or only overlap with another module in a few key aspects, they're like puzzle pieces, and they allow us to sort of rapidly assemble or plug and play these sorts of ontology design patterns, these ontology modules, and put something together quite rapidly. So that's the overall motivation for these ontologies. The work that we do, and especially that I focus on, is on understanding how humans make knowledge graphs or construct or reason or develop or engineer them, right? The modular ontology modeling, I started because I wanted to focus first in my graduate work on ontology learning. Turns out that in those years of 2010 to 2018 or so, ontology learning was really suffering from kind of a lack of success. That sounds harsh, but we were running into issues with the algorithms didn't work particularly well on the available hardware, or natural language processing was still developing and deep learning was just coming into being. And so trying to kind of assess how these algorithms would apply to the area weren't completely clear yet, and so on. And so when we were focusing on this, we were looking for where can we make the most effective improvements for making knowledge graphs as humans, because if we can't expect a human to do it particularly well or in a time efficient or in a sort of computationally efficient manner, how can we expect a computer to do it? And so that's where this comes from, which is a sort of top down, bottom up, iterative loop. So we start with the top level where we try and break things down into conceptual components or key notions. And then you match those to patterns, you instantiate them into modules, and then you materialize them. And then on the other hand, you go back upwards and you try and make sure that you have kept things sort of in line as you're going back up the abstraction hierarchy. So do you have the key notions that correspond to documentation? Are you semantically harmonized according to available ontology standards? And those should exactly map to those same conceptual components in the end. So that brings us to what exactly is modular ontology modeling, and that is MOMO, right? It's a divide and conquer approach. It has 9 steps to it, where we're generally focused on a use case driven aspect where we take essentially the scenario, and then we take the data and the sorts of stuff that is possible and or easy to collect, and we start with that. So instead of focusing on sometimes a more philosophical approach where you might see in foundational ontology such as BFO or something similar Dolce, we focus more on what is possible to collect and how does that impact the sorts of queries or the sorts of scenarios that we want to interact with this ontology or knowledge graph. Momo takes essentially as first-class citizens ontology design patterns. We communicate using schema diagrams, and we create modules from patterns. So whereas there's a very explicit adaptation step. So what do I mean by schema design patterns? In this case, it's just something that is this diagram that we can use to communicate relationships between concepts in a rather human way, very visual, very intuitive. It doesn't really dig down into the different logics or axiomatization that might correspond to what these edges mean. But you can look at this and you can say, well, employees have responsibilities, and those responsibilities manifest as tasks. Tasks are types of actions. Employees have types. You might have a temporal extent, which might be this abstract thing, sort of this model or interface driven or contract driven sort of conceptualization of what duration means. And essentially, they can all be represented as these sort of structural tautologies, which just means that they may be related. So if you're thinking in description logic, this might be like employee subclass min cardinality 0 has responsibility dot task. So it's a very meaningless logical statement, but it's one that can be used to guide that sort of understanding. Like it's meant to interact with this other concept. Probably should have switched this side a little bit earlier, but essentially what we have here are the subclasses. We have the modules. The module is this gray box, and that's essentially going to look at, like, this is a conceptually partitioned thing. All of these things belong together conceptually and are sort of conceptually distinct from task and all of the stuff that goes with that. And then temporal extent is another ontology design pattern, which is defined somewhere else. And so you can look in some other piece of the documentation to find that, but it won't be in this particular schema diagram. So yeah, so bringing ourselves to ontology design patterns, this is a very simple one. Agent performs agent role. It's a sort of disconnect between what a person is and what a person does, or what a thing with agency does versus what a thing of agency is, right? So for example, I am a assistant professor, right? And the English language kind of doesn't really do a good job at disambiguating that verb there. But you can presume that at some point I was a postdoc or at some point I was a graduate student. I am not and not always have been an assistant professor. And ideally, I won't always be into the future, right? And so this essentially attaches a temporal extent, a duration, or a time span to a particular role that I'm playing, which might be the assistant professor. So since 2022 to current, right? Whereas I was a graduate student from 2016 to 2020, and so on. We have collections of these pattern libraries all over the place. We have the modeled, a modular ontology design library. We have the wiki-based patterns library. And we have the common sense micro patterns. You can also go online and find them through like DOSP, I think, through Obo Foundry, because they have the dead simple ontology patterns. There's Otter, the reasonable OWL templates, and then there's ontologydesignpatterns.org, which has kind of like this mixture between very fine-grained, very granular patterns, which we might already call modules, or very specialized patterns, versus very abstract ones like this agent role. And I promise we're getting to kind of the interesting stuff soon. There's just some of this foundational knowledge that we want to get to. So the process of moving from a pattern to a module is called template-based instantiation. And that's really drawing correspondences to things that are very particular to your use case, or very particular to your scenario, or how you want to conceptualize something. So for example, if we go back to this assistant professor aspect, right? We have a person who is the assistant professor. You have a job role instead of an agent role. You have a university that's providing that job role. And maybe we use the date time interval from the XML schema data types for the time period instead of this abstract temporal extent. So it's a very language driven process, right? And for those of you who are thinking forwards, if it's language driven, does that mean we can have LLMs do it? We'll answer that in about 10 slides. But essentially, this template-based instantiation is really about trying to just focus in something abstract to something concrete. And there's not really any guidance in terms of deleting or adding stuff. It's just fine. It's supposed to act as essentially a structure that you use to guide your modeling aspects. And cool. So this is the second to last slide in terms of the modular ontology modeling aspect. So we do this thing called systematic axiomatization, which is for each node in the schema diagram, right? This ARB, this organization employees person. We can do 17 things. There's more, axioms that are out there, of course, because you can specify essentially an infinite number of them, even in track, or yeah, we won't even talk about that part. But essentially, when you're just looking at exactly one node related to another node via exactly one relation, there's 17 pretty common versions of these. Um, and I'm not going to go through them now, but essentially it boils down to like domain and range or existentiality, functionality, these sorts of things, where you can say, well, an organization only employs persons, and so on. It turns out that these 17 axioms are roughly cover, or they roughly cover about 93% of all axioms found in the wild. So if you take a look at like OntoB registry or some of the other ontology registries that are out there, and you just sum up and categorize all of the axioms, these cover most of them. And for an initial sort of taking a schema diagram, the sort of conceptual model that you've built, and turning it into an OWL ontology or a description logic program, uh, that's pretty good first draft. And then finally, in the Momo process, we very explicitly describe that modular structure. We use this thing called ontology design pattern, or ontology design pattern representation language, or OPLA. Could have been called Opal, but we weren't forward thinking enough for that one. But it's essentially a annotation language already specified in OWL, so that way you can simply link things together via these annotations to create these modules. There's some tools out there for this. It's pretty useful, and these are the sorts of things that you would query. You would query the annotations to get the modules out of, and then you can have, for example, an LLM interact with them. Or you might, when you're looking through libraries of these patterns, you can query the annotation languages or the annotations to say, what are all of the modules that pertain to a particular topic or pertain to that include a particular class, and so on. So it's a very useful sort of meta way of already dealing with metadata. Cool. So with all of that out of the way, modular ontology modeling, let's talk about how it actually helps or otherwise impacts knowledge engineering as a whole. So the premise, loosely speaking, is that modules, and very specifically that partitioning of knowledge in a sort of human breakable way, allows LLMs to reason with language instead of with logic, right? So this is really trying to cast stuff back into something that an LLM, for example, is really capable of manipulating, right? They're pattern recognizers, loosely speaking, right? They recognize patterns in language, they recognize structure in language, and they generally seek to manipulate language at a token level in order to produce things, right? And so if we can harness essentially that bridge between the data and the human conceptualization, and when we say human conceptualization, we almost always mean language, then we should be able to hybridize these and come up with a sort of approach that is better than the sum of their parts. So neurosymbolic modular ontology modeling, or ontology alignment in this case. So when we're looking at this, we wanted to think about how you can align different ontologies that are described using a modular structure, and whether or not that modular structure actually helps. So it turns out that there is the GeoLink modular ontology, which has a complex ontology alignment benchmark, which is quite old by now, maybe 2016, 2017. So old in terms of computer science, right? Not in terms of anyone. And it turns out when you try and do this and incorporate the modular information and pass the modular information and the and what you think are candidates for it to be related to, then you can use an LLM to get really, really incredible results. So you can see here that we managed to, or not we in this case, this was Pascal and some of his students, that they really managed to get 104 out of 109 matches between the complex ontology alignment process. This is actually quite impressive. The next runner-up to this was nowhere near close, and in fact, the complex alignment track really suffers from participation in the first place. Anyway, this was one of the very first proofs of concept where we were onto something where it was essentially saying that, oh wow, this modularity is really allowing us to fit specific things inside of a context window. It's allowing us to do sort of natural language processing in a holistic way where we don't have to worry so much about entity bindings, or we can look at some of the composition of complex roles, right? So the classic professor example where it's you have assistant professor, which is a subclass of professor, or do you have like professor has rank assistant and these sorts of things, which are really easy for humans to reason over and understand that they're the same thing. But trying to generate rules that somehow correspond to these on the fly is really difficult. But when you're looking at it from a language perspective and something that's also leveraging a lot of the common sense that's encoded into our natural language, natural everyday language, the LLM really excels in being able to bridge this gap. And when provided with the modular information, does exceedingly or is exceedingly performant. So a little bit on the other hand, we can take a look at how if you have an ontology already and you have unstructured natural language text, such as from a Wikipedia article or just from a report or anything that's just human written, you the modularity allows us to essentially design special prompts or limited prompts, sort of self-contained prompts that allow us to look at guide the summarization of chunks or summarize these papers or these articles or whatever in a very way. So you're essentially doing ontology guided compression, and then you are doing ontology guided extraction outside of the from the natural language. And this helps because at least when this experiment was done, the context window was a bit lower than it was a few, um, than it is now, and so on. And we were able to find the maximum here was about 80, 85, 87, 89% of the triples that were in the ontology were found inside of the text. And this was a proof of concept that we were putting together for this, trying to just understand how effective this might be. And so this evaluation doesn't actually check if all of the information was even present inside of the natural language text, right? So for example, if we're pulling a record of a particular enslaved person, because that's what this next example is. We were drawing from a, uh, a data set that was really talking about the peoples of the historical slave trade, and we wanted to know whether or not um, Wikipedia knew about their birthday. But on the other hand, Wikipedia might not have exactly the same sort of data that the digital historians or the curators or the archivists had, because they had or many more sources under the hood to put into their own knowledge graph, into this own ontology that we developed with them. And so if Wikipedia didn't have it, it came up as a non-match, right? And so even though our ground truth had it, we only matched exactly what was in there, and it turns out in many cases, Wikipedia and the first source or the primary source's ontology did have a really high overlap in facts already, uh, but we were able to extract close to 90% of the relevant facts. So this was super exciting. The general guidance here was this ontology, this prompt engineering guided by the ontology, and essentially just acts more as a mechanism for motivating that modules are important, especially when you're dealing with something that can only remember so far back and suffers from primacy and recency issues similar to a human. So what's some of the other things that we can do with a LLM and a knowledge graph or an ontology? And that's really going to be this human in the loop ontology construction. So this sort of conversational ontologists that we can work with. So in what ways can we variably use this LLM? It fits into all of these different places. So we were talking about how the ontology guided text summarization is helpful. So if we're going to do this in an iterative approach, where at the first step, the humans kind of help us guide or extract the various key notions, and then we use some LLM tool to do some summaries to generate some competency questions for us. We can feed essentially in a step-by-step basis these summaries or these competency questions and pull out the things that seem to be important relative to these concepts and call them the key notions, and we pass them to the LLM. And then we match patterns. That's going to be some sort of external tool, but could also be an LLM based on that first part where we were doing that complex ontology alignment task. And then the systematic axiomatization. So this is where we are. So this instantiation of the patterns, the actual formalization of them according to axioms is really what we're trying to do next. And that essentially looks like this, where we're revisiting that template-based instantiation, where we're trying to essentially cast these schema diagrams into language and then ask the LLM what, given this list of axioms, and each axiom has these different definitions, which of them apply to this simple sentence? So agent performs agent role. Which of them apply? Or conversely, given a scenario and this pattern, can you specialize it into a specific thing? It looks like I am missing my my slide, which had some preliminary results on this, but the instantiation practice was working relatively well with simple examples. And we're still working on different ways to to improve the outcomes for more complex modules. Agent role has four entities in it, but something like the computational observation has somewhere around 12, and the causal events pattern has like 18. And so do we want to sort of talk about the in terms of submodules? Do we want to do this all at once? These are things that we're actively exploring right now. So with that in mind, if we have this conversational ontologist and we have all of these various tools for interacting with natural language, and we have the ability for it to sort of parse the various data that's being captured by various sensors and so on, can we design a conversational knowledge engineering assistant that helps us with our day-to-day tasks? And we would argue roughly yes, right? Based on the various successes in the previous aspects, can we leverage essentially this natural language modality and have it interface pretty directly and pretty constantly with the ontology in a modular based manner? And this is essentially our future and what we're working on right now. So this is ongoing work, and this is kind of what I would like to leave off on in terms of questions or what do we think is going to happen next, and so on. So that's it for us. So really, I guess the question is now, based on everything that I've heard with or talked to you guys about now, is are you convinced? What about this is particularly striking or causes you some doubt as to its effects? And really looking further into, is all of this going to work us out of a job? Don't know. Happy to have a brief little discussion period on this. Thank you.
Thanks a lot, Dr. Shimizu, for this wonderful talk. Yeah, we do have a lot of time for comments, questions, and discussing. Anyone wants to go first?
May I ask some quick questions?
Yeah, go ahead, Jean.
Okay, thank you much. And thank you, Cogan Shimizu. It's a very great talk, and maybe I just missed something, but I'd like to ask some quick question about. I see you mentioned that you have provided module info to the LLM for them to refer and generate some summaries for the chunks of the article in your previous slides. Yes, and I just wondering about the technical details about what is the format, or how did you manage to provide module info to the LLM? Is that through prompt engineering or RAG or something?
In this case, it was primarily it was both, right? So we did prompt engineering and we did RAG, but essentially it boils down to the same thing, because the style of RAG that we did was essentially a prompt injection. So if you can see here on this slide, we have this slightly smaller picture here in this top right, which is the enslaved ontology, or in the enslaved.org ontology.
Yes, that's another question I'd like to ask. Given the structure of this modularized ontology is really complex, how did you manage to ensure that you can convey all of the available information through the prompt engineering? So the too lengthy prompt might lead to, say, the LM tend to forget the details.
Yes, so exactly. So we essentially, what we did is, when you summarize according to a particular module, you are generating a chunk, and then you are taking that chunk and passing it in. So it's not like you are taking the entire ontology at the same time, right? Because as we've noticed, things in the middle of the context window tend to get lost, and especially if your prompt is very huge, things are ignored. So you're looking at, okay, so I take this module here at 3 o'clock, right? And I pass it into here, and I have my example that corresponds to the module, and I ask it to summarize, sorry, not just a summarization query prompt, plus the modular info, say, for this thing here, which I think is event. And
And
you say, okay, summarize the article according and only according to the event module. So it'll strip out a lot of stuff, right? And then you take that module info again, and you'll have a example that corresponds specifically to that module, and you query for the triple extraction.
and how did you manage to query the relevant module info from that entire ontology model? Are you using
Well,
cosine similarity or?
no. So modular structure is human defined, and there are annotations inside of the ontology that you use to extract a single module. So you can query and say, for a particular class, find all things in the module that it belongs to, and that's your module. So
And
there's an actual metadata layer, right? That says X is a module X, and then concept A is native to X, and concept B is native to X, and these sorts of things, which would be, yeah.
yes,
Does
but
that help?
well, maybe I can make my question more clear. I'm sorry. I'm just wondering, given a certain document chunk from, say, Wikipedia, how did you determine which part of the modularized ontology is relevant to that piece?
We did not. No, you take the whole chunk.
Model. Uh-huh.
Yeah, you take the whole article, or if even if that's too large, then you chunk the article just sort of arbitrarily, and
Yes.
then you pass it the modular information. So the idea
The
is not to, okay.
I'm sorry. The entire model or the modularized one?
The specific module.
And how did you determine that specific part of the module?
I am okay. Maybe so. For each chunk, you
Uh-huh.
do this with every module.
Oh, I see.
Yes.
And you rank the results, or?
Yeah. So sometimes it won't the summary may not produce anything, or it might come back as non-relevant, or it gets the next step and then no triples are extracted.
Okay, understood. So this part of the work is kind of involved with the human in the loop manners?
Yes, so at no point are we looking at this stage at a fully autonomous pipeline. This is purely a human in the loop process.
Okay, thank you.
I at least on my side, I don't see a near future where we trust LLMs with
Yes, only
formalized
my
knowledge.
yes,
Yeah.
I totally agree with you. And I have another quick question. Say,
Uh-huh.
the modularized ontology is really a very promising aspect and very highly resonate to my own idea. But I'm wondering, do you have the plan, say, convert the existing ontologies into modularized ones?
Yes, so we're working on various ways of doing this, and this work that we started here with the ontology alignment is the first step in this, because if we can show that it works pretty between two modular ontologies, can we somehow do the
I'm sorry, your Zoom seems frozen.
Yeah, he seems frozen.
Just wait a moment. I guess we'll come back.
ontologies don't use a foundational ontology. It tends to be a little bit here to modularize, because from trying to determine which level of abstraction. So if you're operating on the level of endurance or perdurance, the patterns look very strange. But if you're looking at a little bit more empirical, something that's closer to I don't know, like SOSA or SOSA SSN, right? That tends to be a little bit easier to modularize, because you can kind of look at the instantiations of observations kind of as a gestalt, right? Or different instantiations of observations are easier to kind of partition or compartmentalize, um, and so on. But I would just say that the trying to take existing ontologies and turn them into modular ontologies is a piece of ongoing work.
Okay, thank you.
Thank you.
Okay. Thanks, Jim, for those detailed questions. Or do we have anyone else who wants to give a comment? Oh, John, I see a hands up.
Yeah, just on this slide that we're looking at, can you say a little more about the green and the yellow and the red? And I just found this slide went a little faster than my brain could go today.
No,
So if you could talk
no
a
problem.
few more minutes about it, I'd appreciate it.
Sure, I can talk a little bit about this. This slide almost entirely comes from Pascal's work. So if you are still unhappy with my explanation, go yell at him.
Or read the paper is another option.
Yes, yes. But essentially what these are things that they're different results, and essentially it was given a module called award, what concepts in the ontology, the GMO ontology, relate to the this specific award. And the green is
you mean to the idea of award in your module?
yes, correct.
Yeah, right.
Yes. And the green means a full match. The yellow means it was there. It was it was shoot, now I don't remember.
The reason I was asking is I guess I was unclear on whether the text that I'm seeing was generated by the LLM or was generated by a person based on what the LLM did.
Yeah, the text was generated by an LLM and the highlighting was done by a person. And now I remember. So the yellow, if you look here at this award top, there was award amount, and then there was has award amount. Award amount existed, has award didn't. right? And so it's kind of like this semi-match where it was close enough. And then when we were looking at person, these things, this personal info item, person item, they did not exist. They were pure hallucinations from what I
Wow.
recall from the
I
slide.
see.
And
Wow.
so for the most part, so person was one of these detected without module information. That's essentially the part one of these 5. And then the greens were like, okay, cool, we got this match between the ontology and the module.
Mhm. Mhm.
Um, but yeah, I would recommend taking a look at the paper. It did actually get published, so the reference here is in ArcZiv, but the paper was published in, excuse me, KGSWC last fall.
So at the risk at the risk of oversimplifying this, do I understand correctly that a fair bit of the process that you've been talking about, I think I get the modularization part, but the thing that connects it to the large language models is the ability to readily translate whatever's in the modules to text equivalents, that the triples are being translated into the text and the large language model is operating on the text? Or is it in
Yeah.
fact that the large language model is seeing nothing but RDF and is proceeding from that and can give its output back in RDF without any intervening actual text labels ever coming into play?
No, it's operating almost entirely on language, or something very similar. We tried with RDF, didn't work. LLMs
They can't figure it out.
yeah, RDF XML not good for
Mhm.
anything except for toy examples. Turtle tends to be a little bit better, but there's still sometimes some syntax weirdness.
Mhm.
Like periods and commas get confused a lot, or at least in the models that we were using at the time.
Mhm.
And so what we wound up doing is we wound up using a sort of functional syntax
Mhm.
because it excels generally on code. And we went with that, where essentially it, or more like a data log functional sort of thing, where it's like the triple is relation parentheses a comma b, fill in the blanks, right? Which is something that LLMs tend to be pretty excellent already, where it's here's a pattern, fill out the pattern. And so in this case, it was here's this conceptual item, the predicate, fill out the pattern such that A holds for this predicate. And it that worked. That worked quite well, actually.
Okay.
Yeah, I also have a, oh, sorry for,
No,
I
that's
also have a follow-up question here. So, and also for the output, because I think John and Kogan, you were just talking about like the input, the data source, and then for the output, Kogan, have you ever had any experience like using large language models to output like a module ontology or just like a part of a knowledge graph? So using large language models to output ontologies written in RDF or Turtle, or using large language models to write Sparkle queries. Have you ever had any of those kind of experience in your work?
Yes. So trying to go directly to the turtle. So let's see. Somewhere in here I mentioned, oh, we're going the wrong way. This one here, this common sense micro patterns, where essentially we're trying to output ontology design patterns. So take in a concept and maybe a little bit of guidance, output turtle. And we did this like 6,000 times. Very wild results, right? Sometimes it was really good, sometimes it was really bad. We tried 10 different prompts, and the quality was really high variance. And that was both conceptually and syntactically. And the syntax errors were always very difficult to track down, because it was sometimes it would output a prefix that didn't match the rest of it, or sometimes um, the big one that I really remember was commas and periods. It would just end a triple and then put in another thing after the period. Doesn't work. So we ran into some of those problems. I don't have a good example or a good idea of how to improve that, except for don't use Turtle or RDF. I don't think it sees enough of that. So put it into something language-based that you can very purposefully translate out of. That's in these things. Probably I would use a data log like syntax or rule syntax, because then you can just R to RML it directly into syntactically correct RDF or Turtle. When it comes to competency questions, or sorry, Sparkle queries, this one we've had a lot more success in if you ignore prefixes. So if you're ignoring prefixes, these tend to be all right. And right now we're working on a couple of avenues that are focused on what information do you need to include in your prompt in order to guarantee that you have a good Sparkle question or a Sparkle query. And we're slowly ramping up. So on simple ones, you just put the whole ontology into it, and it can generally generate a correct Sparkle query. It doesn't necessarily do as well with complex ones. We haven't tried these disjoint versus union or intersection style Sparkle queries. But then again, a lot of people would argue humans shouldn't be writing those either because they're very slow. And so there's a little bit of rhetoric around that, but stay tuned out of my lab, I guess, in a couple months, and hopefully we'll have a good publication or preprint on the sort of agentic query RAG thing that we're working on.
Great. Thanks a lot, Cogan. Thinking about time, I think we can wrap up in here. And thanks again for the talk and also those active discussions from the audience. Wei Ling, can you stop recording?
Sure.